Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. My name is Jim Chastain. I'm with the Applications Engineering Group here at EasyPower. Topic today is how to reduce the cost of your arc flash study. Specifically, a couple questions have come up in the last couple weeks regarding how to reduce the cost of a study, and so it's prompted this presentation. So welcome to the conversation. We may be constrained on time today, so any questions would be answered if you'd want to submit them via email. And let's jump into the topic. So the agenda, to start with, we're going to talk a bit about some terms that came up out of the last discussion on low voltage, and we didn't quite cover as completely as I would have liked. And then we'll jump into the two case studies. The first is the example of a low voltage system which had a large number of installations, all 208 volt panel systems, and the way that they undertook the procedure to reduce the cost of those studies. And then the second one is in a 480 volt system which had a large number of motor loads on bus ducts drops, and how they dealt with reducing the cost of data collection. The primary emphasis is to show how to use the tools and manipulate the model to better understand the constraints of your system, not so much to deal with the regulations. The regulations are what they are, but the better we understand the system, the better we can deal with those regulations. First, let me say the following information is not a recommendation for any specific facility or study. We're describing here two cases where facility engineers have been able to develop a practical approach to the compliance by using EasyPower tools to learn more about their facilities. So this may or may not be appropriate for your application, but certainly the way it was done, I think, is useful to all of us. So before we jump into that, let me talk a little bit about short circuit current rating. There are two terms that sometimes get confused or misapplied. The first is interrupt rating, sometimes called ampere interrupt capacity, and it pertains to a component. And in essence, it's the highest current at the rated voltage that the component will continue to perform per the datasheet specs. Generally, it's tested by the manufacturer in some way or form, and frequently on the datasheet, we are given the conditions of those tests so they can be duplicated or taken into consideration in our system. Now, an SCCR rating is essentially a short circuit current rating, and that term is applied primarily to assemblies or assembled parts or subsystems. There are multiple ways to kind of deal with that rating. First is to test each unique combination of parts and see that it meets some certain spec. Another way is to previously test the subsystems and then assemble them, and in which case we basically rate the system, the total assembly, at the weakest link that has been tested from the individual components. Well, in terms of arc flash modeling, EasyPower accommodates both in terms of the way the data can be entered in the one line. Each device, we can designate the interrupt rating, or if it's a panel, we can designate the short circuit capacity rating. And in terms of evaluating that, Smart Duty, which is a feature that's built into EasyPower, will indicate when the weakest link is the limitation in the short circuit study. So what you're going to see as I jump into the tools is first I'm going to set the threshold on the one line to display the parts that I want to consider. Then we're going to look in detail at those parts by using the equipment duty report. And then I want to take a step further and suggest that if I use the template for equipment to properly enter those data points, it will save time in the long run because the data would be set up at the time I do the modeling. So Let's jump into EasyPower and see how that's done. Here we have a one-line diagram, and I've got all the data entered, and I'm ready to do a short circuit study. We enter short circuit focus. We look at half cycle current. We fault all the buses, and notice that we get branch currents on each of these feeders. And then this flag right here on the second row is called equipment duty. We invoke that, and we see several numbers are red, and they range from a -3 here up to a +48. Well, these are set up, or basically have exceeded a threshold that's set in my short circuit options tab. The control setting here on the left, the equipment duty threshold is set at a -10. And what that means, anything that's negative, it's below the compliance point. It's got how much headroom. So in essence, this breaker has 3% headroom before I'm exceeding the spec. The positive numbers show that we violated the specification, and that's how much excess current is being applied to that component. If I want to look at more elements in the system, I might lower the threshold. So instead of a -10, I might say -55 or 54. And if I apply that, I notice I gotta make it a -55. So we have a lot more components show up, all of which are negative numbers greater than 10. And there are some cases where I might want to look at that. But for now, let's just consider things that are within 10% of their threshold. All right, so first of all, let's look at these two breakers here. First of all, there's not a number here, which is suspicious, and the number here is 12%. The details of the devices that are failing will show up in my reports. If I have requested an equipment duty report that includes all violations and warning, only violations and warning devices, it'll show those elements to me. Otherwise, I might want to include all devices. So let's look at that report, which is on my list of windows, equipment duty. And we look at BL2A, which shows it's a Cutler hammer breaker. It's rated for 14,000 amps. It's being exposed to 15.7. And if we look at BL3A, which is the one next to it, it's rated for 12,000 amps, and it's being exposed to 13,000. So in both cases, it's well over the violation, the compliance point. Let's go back and look at our current and see where this is coming from. If we look at this leg that BL2 is in, we show the maximum current that will pass through this breaker if this bus faults is 13,827 amps. So how did we exceed the 14,000 amp rating that's on this device? Let's kind of go back and look at that. If I look at my data setup for this breaker, my short circuit current rating is 14,000 amps. If we're only exposing it to 13,000, how can it be in violation? Well, let's look at this one more time. So let's look at our fault current. When we do a short circuit fault current, if this bus were to fault, it'd see 15,600 amps from the supply side of the utility. It'd see 52 amps from this leg, 52 amps from this leg, and 52 amps from this leg. In total, that bus would see a total bolted fault current of 15,773 amps. Well, it turns out to be properly rated, this assembly needs to be able to have every element that's plugged into it accommodate this much current if a fault were to happen just downstream of this particular breaker. And if you look at the quantity that would remain if we took 15,773 and subtracted the 52 amps that are being forced as feedback, then this breaker has to handle that much current in reverse, if you will, or as a fault. if the fault were to exist right just below the breaker. So that's why this breaker is not rated or not properly meeting its short circuit rating. And frankly, it's the weak link for this whole bus. Now, if we go back and look at this other breaker that we didn't see a number on, and open up its, go back to database edit and open up the breakers, well, you can see right away it doesn't have a part number, which probably means we didn't properly set it up to start with. And the only reason it has a 0 interrupt rating, so it's a lost cause any way you look at it. All right, so let's go back and look at the other side of our fault. Here on the this panel, the panel says it's overrated by 48,000 amps. So again, let's look at our database and see where things are going awry. For our basic panel, we have it set up for 42,000 amps. Okay, that's the panel itself. Incoming, we see a device that's set up for 22,000 amps, so that doesn't seem like it's out of order. If we go in and look at the individual breakers, the protective devices here, everything on the left side is 18,000 amps. Let's look at the right side and the protective devices, and sure enough, here's a device at 10,000 amps. So again, this is the weakest link for this whole panel, and consequently it's being flagged as a non-compliant component in our one-line diagram. So what we've seen is how to use a threshold to look at more or few of the non-compliance. We've looked at the equipment duty report to see what's really going on a particular panel. I wanted to show on the template, and we're talking about buses now. If I go to the tool tab here at the top, go to a bus setup, this gives us the ability to control the default settings when we use a panel. And here, if we know we're going to be using a lot of square D panels that we have a specific rating for, we might want to just set up square D with the ratings, the most common ratings on our panel, and thereby have that information already installed as we go to set up the next set of panels or of buses. So the point is, by doing that, we eliminate the need for having to catch these near misses and have a more complete one line as a result. All right. So moving on, let's talk about our first case study. And now the situation occurred with a very large U.S. company that has multiple plants and multiple installations. They'd completed the arc flash hazard assessment for their large facilities, but they understood that they have over 2,500 small standalone 240 volt systems, and the cost of doing studies on each of these standalone installations is prohibitive. So the request was, how do we handle the labeling requirements? Well, because these are all above 50 volts, they need to have a label on them. And unfortunately, they fall into the realm of the least accurate part of the 1584 model. And so consequently, there's kind of vague guidelines on how to deal with low energy, low voltage systems. So facilities engineering came back with a solution, effectively a study that provided a way to qualify and add additional understanding to the systems that they had to deal with. And so they developed a profile of the system parameters and created a decision tree and trained the technicians to use for all these 240 volt panels by being able to, if you will, address the needs of an individual panel based upon the incoming service labeling that's already there. Now the standard daily wear for technicians in this case was 4 calories. So the concern was where, if any place, do these systems require greater than 4 calorie PPE. And so what we've discovered, or what was discovered, was better knowledge or better awareness and consequently better training. And so it all centered around an evaluation that was done of a typical system. So let's jump into EasyPower and discuss it. So here was the kind of the test subject that they sample one line that they came up with, and a typical service entry for a 400 volt panel, excuse me, a 240 volt panel would be about 25,000 amps. And if they looked at the short circuit currents available, they found that invariably the typical amount was in the 23 to 25,000 amp range. And given that each of these panels was supplied by a Mulder case circuit breaker, that calculating the instant energy there would give them better than, almost invariably, something less than 1.2 calories per square centimeter. Well, in the case of the worst case available current, they set up a scenario. Then we could go in and look at, I guess I need to do it in my database edit. Look at a scenario that was set up for worst case. And in this case, the highest available current was 45,000 amps maximum. And the worst case, or the short circuit current in that case, was just under 40,000 amps. And at that rate, even a typical, if we look at other possible impedances, at that rate, the worst case instant energy was still less than 1.2 calories. And at lower currents, it declined or decreased enough that they were virtually not a concern. So the high end of the current range wasn't a problem as long as the Mulder case circuit breaker operated normally. So the problem, or the real consideration, was how to ensure that we have the Mulder case circuit breaker operate in the instantaneous range. And to do that, let's go back to our base case, go into coordination, and we actually have already set up a plot for this. So where we have the typical value, or the high-end value of 23,000 amps as a fault current, we know by plotting that curve for this 400 amp breaker and then inserting the arcing current, that the 100% arcing current would be somewhere around 8,400 amps, and it clearly falls well below the 2-cycle line, which is 0.033 seconds. So the problem comes, or occurs, when we have a situation where we're much lower. And in this case, we fault the current of 10,900 amps, and we see that our arcing current falls on this vertical band. And what that means is that we know the arcing current that forms under these conditions, the maximum it would draw, would be something over 4,129 amps, according to the IEEE model. If the worst case incident energy is created at the 85% arcing current, then that's what we must use to do instant energy calculation. So the problem is it falls in this vertical band, which means the point at which this fault current, this arcing current, intersects the right-hand side of our trip current, that's the time we must use for calculations. And when we do that for instant energy, when we do that, we see that we have an instant energy that measures out at over 125 calories, which is totally unreasonable, but it's what we're left with in terms of what the standard allows as far as calculations. 4,000 amps is on the hairy edge of being non-self-sustaining, but according to studies, it still has the potential for sustaining for as many as 3 or 4 cycles. So that brings us to the point of what is the minimum amount of current at a fault that would guarantee that we fall into the instantaneous range on that trip curve. And with a little bit of playing around with the impedance, we find that this particular value of, if I look at the current, arcing current would be 11,999. Now you might say, Jim, you're showing 11,990 here, but over here you're showing 12,087. Well, the issue is, or the difference is, on the plot we're showing the asymmetric current, and on our one line, if we look at our options, we're showing symmetrical current. If we were to show asymmetrical current in both cases, you'll see that it pretty much matches 1209 versus 12087. All right, the bottom line is, though, that's the point that we get the highest or the lowest current, and we can still fall below this vertical column. And if we look at the instant energy here, we have the 0.6 calories. So any current between this 12087 and the maximum that we got from our current would guarantee that we have a 2-cycle clearance, and consequently the instant energy would be much less than 1.2 calories per square centimeter. So where does that bring us in discuss? So again, he didn't deal with the constraints of the standard. He didn't complain about this 85% arcing current. What he went in and did, this facility engineer, is took a hard look at what his system actually consisted of, and as a result, he came up with a decision tree to train his technicians to be able to look at what the available fault current was coming into the facility at the 240 volt level, and then be able to determine whether they needed additional PPE. So we ended up with more knowledgeable field technicians and had to potentially eliminated over 90% of the data collection that would have been required had they gone to each panel and collected data and done the study. And as it turns out, most of the panels do not require PPE beyond the daily wear. And I can't even guess how many tens of thousands of dollars he saved in the process. But frankly, I think he deserves a gold star. Now the second case is a little bit different because it's on a 480 volt bus system. In this case, this was a large manufacturing plant. In fact, they had several facilities, and in each facility, they had multiple bus ducts that ran the full length of the production line, and each of these bus ducts fed hundreds of floor tools and motors. Most were 50 horsepower or less that were connected with variable cable links. Well, to collect the data on all of this equipment, they would have to, especially up on the bus duct, they already understood that that was a dangerous area in terms of arc flash. They would have had to de-energize the bus duct, move a lift to each drop, open up the fuse cover, and record the data both at the fuse and or if it's a multi-case circuit breaker at the drop, and then move to the next one. And consequently, they didn't have the bandwidth, the personnel, or the shutdown time that would allow them to collect that data. So they needed to label all the loads on the floor, They knew that they had they cordoned off the bus duct so that nobody actually accessed it during energized conditions. And so it was one thing to put a danger label on the bus duct. It's another thing not to label the motor drops on the floor. So again, what the facility engineer did at this point is approached us and said, hey, is there some way we can look at the possible combinations of components that we have in the system and bracket what the worst case and best case arc flash would be? And what we helped them to do was to set up a study that considered a worst case available short circuit current ranging from 15,000 amps to 42,000 amps, and then varying cable sizes ranging from a size 10 up to a 4/aught, and then charted the response or impedance, in this case from 30 feet to 300 feet for each of these combinations, and then look at, or at least consider, whether or not they were being supplied by a molded case circuit breaker or by fuses. And then we charted by all these parameters the incident energy based upon the cable run that was being supplied to the motor drop. Now, one of the first things that popped out as we started doing the study is that because all these motors were less than 50 horsepower, that anything below 150, as shown in the example I'm about to show you, was insignificant as far as moving the dial on the arc flash incident energy. And so all of these considerations were made at no motor contribution. So here's the simplified case. Now, the reason for showing this to you is that this study and the methodology here, I think, was rather clever, but it reduced the cost of doing the study by a considerable amount, primarily in the form of data collection. Again, because it involved a lot of equipment on their part and a lot of downtime to be able to collect the data that we were considering. So once we set up the simplified circuit in EasyPower, we were able to change all the variables and then plot the results. And the resulting table basically indicated that more than 250 cases were studied, and the results indicate that the arc flash energies at the individual motor switch box or sub panels through a motor protector fed from a motor control center, a distribution panel, or a bus duct with the following range of currents would be less than 1.0 calories. And these were the days 10 years ago or so where we were still using class category PPE ratings, and ultimately that's what they were able to utilize for their results. So as a result, they used a table lookup then for their site-specific labeling, and it did save hundreds of hours of data collection. And what I'm suggesting is that this particular study, because it was not contracted by the client, it was proposed as an exercise that we engaged in. We make this information available, less so for the results of the data, because again, this is dated in terms of the class of PPE, but more in terms of the methodology. And so in the handout box of the webinar control panel, there is a handout that is a PDF of this particular study that you're welcome to download. If for some reason you cannot access it, you're more than welcome to contact me, Jim, at EasyPower.com, and I'll send you a copy of it. Now again, this information is not recommendation for any specific facility or study. We're describing these two cases where the facilities engineers have been able to develop a practical approach to compliance by using EasyPower tools to better understand the systems in their own plant. What you'll see is that the name of the study is Arc Flash Energies at the Individual Motor Control Switch Box, and it includes the study description and the results. Again, if you cannot get it out of the webinar control box, you're more than welcome to contact me at jim@easypower.com, and we'll send you a copy of it. Appreciate the time and attention for joining us today, and look forward to talking to you down the road. And again, any questions entered will be responded to via email. Have a good day.